in the case in which, so separability is defined as whether or not there exists a hyperplane between the positive and the positive examples and the negative examples. So if a separator exists that's correct for all the training data points, then they're separable. And there's a guarantee that in the binary case, the Perceptron algorithm will always find this hyperplane. We'll always find the hyperplane that does separate the points. It actually turns out that in the multi-class case that this isn't true. And it won't always converge to the correct answer. And you can also, there's one more property. So we just talked about the convergence property. There's also a property which is this mistake bound right here. And what's a mistake? A mistake is when the algorithm, when your weights incorrectly classify the data point. And you can actually bound the number of mistakes that your algorithm will make over the course of training. And why this is important is at each time you go through the data, you're going to have at least one mistake until you're done. So this is actually bounding the number of total passes you have to go through your training set. So this is how long it's going to take for you to train your algorithm. So what this says, you don't need to know how to derive this, but K in this case is the number of features that you have, the dimensionality of your features, of your feature space. And delta, so the more features you have, the longer it might take, and the more mistakes you'll make. And then delta is your margin. So in this separable case, if you have your margin is defined to be the distance between the maximum distance between all of your positive data points and your negative data points. So this is delta. So the bigger your margin is, and the easier it is to find this plane, and the less mistakes that you'll make. So this does make one assumption, and that is that all of your features lie in this in the interval -1 to 1. So essentially, if you scale all your features to be between -1 and 1, then this is the bound that you have. If you don't want to make that assumption, then what it turns out to be is that K is equal to the radius squared of the sphere that encapsulates all your data points. So you might say, why can't we, if we just have this margin, why can't we just make all of our data bigger? Then you'll have a bigger margin, and it'll be easier to find this hyperplane. But it's still the same problem. It's still the same difficulty. So in that case, your K is equal to if all of your data points lie in some sphere, then, and the sphere has radius r, then r is equal to the square root of K. Any questions on that before we move on? Yes?
If your data is not separable, could you just add more features?
Yeah, so the question is, if your data isn't separable, can you just add more features? In some cases that will work. It depends on what the features are. So it's possible that in the current space that you're in, it's not separable, but when you increase the dimensionality and put it into a higher dimensional space, that it becomes separable. It's not always, it'd be great if you can find a feature space that it is separable, but it's not always possible to find that. And it's also possible that once you get to a higher dimensional space, then you might be more likely to overtrain to your data and overfit. And we should talk, I think they'll talk about that on Tuesday. So in the case where you have non-separable data, you have your examples right here, and then you might have one example right here. It may be that it's incorrectly labeled, or maybe that this training point is just an outlier. And what your algorithm will do is it'll just keep on thrashing around and finding a ton of different hyperplanes, but it'll never end up because there will always be some error because it's not separable. So these are all the hyperplanes that it might go through, and there's a couple of ways to deal with this. One is just sort of a hacky way, and what you do is this is called the average perceptron, is to just take the average of these hyperplanes, and you'll get something like this. And turns out this works pretty well in practice, but it's not completely satisfying because you don't have any guarantees about this, about what hyperplane you'll end up getting. And in this case, it's possible that it could do better on the training example, on the training data that you got, because if it instead found this line right here, that might be better than the line that you found right there.